let's now just look at solving quadratic equations, which of course we know how to do. X squared plus 3x plus 7, we'd say what multiplies together to give 7, adds together to give 3. We got a problem. Now in the past, the reason we have that problem is because we have the square root of negative 19, and we couldn't simplify that surd. But now we can simplify the surd because we know what the square root of minus 1 is. So I can rewrite the square root of negative 19 as the square root of 19 times the square root of minus 1. I know what the square root of minus 1 is, it's I. And I now can come up with a solution to this quadratic. Minus 3 plus or minus root 19i. Some people prefer to put the I out the front so it doesn't look like you're saying root 19i. As long as I guess it's clear that I is not included there under the square root sign. So there's our two solutions. Another way you could do that now is by completing the square. Every quadratic equation now can be solved by completing the square, because every quadratic equation can be written as the difference of two squares. X squared plus 3x plus 7. If I was going to complete the square, I'd say x plus half the coefficient of x, so 3 on 2 all squared. But if I was to expand that out, I'd get 9 on 4. I want 7. So I need to add another 19 on 4. Now in the past that was a problem because that's not the difference of two squares. But it is now, because 19 on 4 I can write as minus 19 on 4 I squared. It's now the difference of two squares. So I can say x plus 3 on 2 plus root 19 on 2i, x plus 3 on 2 minus root 19 on 2i, and we come up with the same two answers. So whichever method, I mean that's your choice of course, how you prefer to solve quadratics, but you now have that option of simply creating the difference of two squares and factorising. So creating quadratic equations. All quadratics that have real coefficients. So if you've got a quadratic equation and it's got real coefficients, will have conjugate pairs as its solutions. Because if you think about the quadratic formula, you're always going to have plus or minus the square root, so the imaginary part. So you'll always end up with conjugate pairs. Let's just prove that a little bit here. So x minus z times x minus the conjugate of z. If I was to expand that out, I get x squared minus z plus the conjugate of z, x plus z times z conjugate. Well, z plus its conjugate. If you add a number with its conjugate, the imaginary parts will disappear because one's plus, one's minus. You'll be left with twice the real part of the complex number. And then z conjugate, remember we said, oh, well, that's the sum of two squares, x squared plus y squared. So if I now want to create a quadratic equation whose roots aren't real, whose roots are 4 plus I and 4 minus I, it's not a problem. I know the sum of the roots will be 8, twice the real part. The product of the roots will be 17, the sum of the two squares. 4 squared plus 1 squared, 17. Therefore, I have my equation, x squared minus the sum of the roots, x, plus the product of the roots. So how do we find square roots now? That was fine whilst we were dealing with real numbers. Find the square root of 16. Oh, 4. But now, if I'm dealing with imaginary numbers, how do I find the square root of an imaginary number? I'm going to show you a couple of different ways. I could square both sides, because this is probably going to be easier to find. And on the left-hand side, it becomes a squared plus 2abi plus b squared, and I can equate. The real part equals the real part, and the imaginary part equals the imaginary part. Okay. So if the square root of x plus iy is a plus ib, I'm not going to waste time doing that working out each time. If I've got to find that square root, I know that, oh, okay, well, of what I'm trying to find the square root of, the real part will be a squared minus b squared. The imaginary part will be 2ab. I'll do that every time. So if it's minus 12 plus 16i that I want to find the square root of, well, I know a squared minus b squared will be the real part, negative 12. So then 2ab will be the imaginary part. On the right-hand side there, I'll rearrange that. B is 8 over a. Sub it into the first one, and I get a quadratic. Well, it's actually a quartic, but it's a quartic that I can solve like a quadratic. There we go. Multiplies together to give negative 64. Adds together to give 12. 16 and negative 4. So either a squared is 4 or a squared is negative 16. But remember, a is a real number. So a squared can't equal negative 16. So a is plus or minus 2. When I sub that into b, I'll get plus or minus 4. So I now know that the solution is 2 plus 4i plus or minus. Now, here's the difference. If I said to you, what's the square root of 16? You would give me the answer 4. Okay? You wouldn't say plus or minus 4. But remember, complex numbers or imaginary numbers can't be ordered. So when I say the square root of negative 12 plus 16i, I don't know whether it's 2 plus 4i or whether it's negative 2 minus 4i. I can't tell which one's the positive. I mean, I suppose logic would say the positive square root would be when they're both positive. It would seem logical. But what would happen is, if instead I had 2 plus 4i, I had 2 minus 4i, which one would be the positive solution? Is it the real part that needs to be positive, or is it the imaginary part that needs to be positive? We don't know. Some books will define it. And I think Patel defines it as the square root, the positive square root is when the real part is positive. That's just a definition they've done for their text. So when you're looking at those answers, you'll know that. But that's not an actual definition as such. So we just say, well, plus or minus 2 plus 4i, because we say, well, there's 2 square roots of these. Okay. A plus ib is the square root of x plus iy. Here's another way of doing it. So we just saw that a squared minus b squared was x, and 2ab was y. If I play around with this, now again, you don't have to do this algebra each time. This is just to prove what I'm about to do. X squared plus y squared would be a squared minus b squared squared plus 4a squared b squared. So I end up with a to the power of 4, 2a squared b squared plus b to the power of 4. So watch what happens. If I know the square root of x plus iy is a plus ib, then I can say a squared minus b squared is x, the real part. A squared plus b squared will be the square root of that sum of 2 squares every time. By the way, if you're working out whether they have the same sign or not, it all comes down to the imaginary part. If the imaginary part is positive, then a and b will have the same sign. If the imaginary part is negative, then a and b will have different signs when you're finding square roots. So, all right, same question. Minus 12 plus 16i, but look how much quicker this is. A squared minus b squared will be the real part, minus 12. A squared plus b squared will be the square root of the sum of 2 squares. Okay, 12 squared, 144. 16 squared, 256. Add them together, you get 400. Square root of 400 is 20. You've now got a couple of very simple simultaneous equations to find a and b. 2a squared is 8, so a is 2. Therefore, b is 4. The imaginary part is positive, so they are the same sign. So it's plus or minus 2 plus 4i. There's your answer. Okay. Now, I don't know that that method's in a lot of textbooks. Might be now Cambridge, I'm not sure. But certainly it's a very quick method to doing it. Let's find this one. Square root of 5 minus 4i then. So a squared minus b squared will be the real part. A squared plus b squared will be the sum of 2 squares, square root of that. 5 squared is 25, 4 squared is 16, 25, 16, 14, root 41. A little bit harder with this one, you'll notice. 2a squared, a turns out to be, look at that one, half the square root of 10 plus 2 root 41. So therefore B turns out to be a half the square root of negative 10 plus 2 root 41. So there's my square root of 5 minus 4i. Plus or minus a half square root of 10 plus 2 root 41. The imaginary part's negative in this one, so it'll be minus I root. That is a correct answer, by the way. But it's probably easier to work out the first way we saw it. What is the difference? The difference with the first one was we were dealing with numbers that create a Pythagorean triad. Remember those magical numbers, a squared plus b squared, c squared, they all turned out to be whole numbers? So the very first example I did was nice, because I had 5 and, what was it, 5 and 12, or? What was it, 12 and 16. Okay, they're part of a triad. 4 and 5 are not. Well, yes, 3, 4 and 5 are. So if I had 3 and 4 there, that would work out nice. 4 and 5 do not work out nice because of that. A squared plus b squared is root 41. So if the sum of two squares, when you square it, turns out to be a nice whole number, that method's very, very quick. If it doesn't turn out to be a neat whole number, you can see you get something that looks quite ugly. It's correct, but it's very, very ugly. Let's solve this equation. Okay, it's a quadratic. What multiplies together to give 2 minus 2i, adds together to give 2 plus I? You can take a while to think about that. It does work, but let's just go straight to our formula. Negative b plus or minus square root of b squared minus 4ac. Square root of minus 5 plus 12i. If only we knew that. By the way, 5, 12, Pythagorean triad, 5, 12, 13. So that will work nicely using the other method. So let's just go find it. A squared minus b squared is negative 5. A squared plus b squared will be 13. A is 2. B is 3. The imaginary part is positive, so they'll have the same sign. So it's 2 plus 3i. Play around with that. There's our answers. All right. 1b.